on quantitative methods for HIV research. So this section is going to be on statistics. So we'll be going over some basics and then going into some stuff involving prediction and, kind of a little bit of machine learning. So we'll kind of briefly talk about random forests and whatnot in the back half. So I'll be teaching today's session, and the remaining will be taught by a Pishu Shi, who is associate professor here at Duke in the biostat department. So first off, what we want to make sure that we do is get hooked up to the DCC on demand. So hopefully everyone has access to that, because that'll be important. So if no one, so you're good. What was it? Sorry. Imani. Oh yes, sorry, emails. Are you good? Awesome. So once we're hooked up there, we can kind of go from there. So show on Zoom any problems with the DCC and hooking up there. Okay. No? So as a reminder, if you're on DCC, you want to click on Interactive Apps, click on the CHSI RStudio Workshop, kind of leave the wall time and whatnot as is. For this account, it's going to sometimes auto to 2023. You're going to want to click on 2024, and then you're going to click Launch. So I already have one running to go to. So all good on there? Are people able to get access to it? Yes, yes. All right. So once in there, we're going to, basically, if you haven't cloned the repo, we're going to clone the repo into this DCC RStudio container. So show of Zoom reactions or hands if that's going good, and it's in the room, everything's good. You should be good.
Yeah, we're gonna have to repull it.
Yeah, so everyone's gonna have to repull. Awesome. So I'll let everyone do that quickly. So once you open up, so let me close this. So if you're in the DCC on demand, when you open it up, it's going to look like this. So Peruzi, do you see kind of what I have here, this kind of open RStudio? And what you're going to do is click over here. And then if you were in last workshop series, you should see the repo in there already. If not, you're going to want to create a new project. So I can't remember. Were you here last year, Peruzi? Last workshop series 1? Okay, yeah. So you should then just click on the one over here that corresponds to last year's. And once you do that, so mine is 2024, 2025 copy. Yep, that's it. And then once you're in there, there's going to be a little bit of loading. And then, oh yeah. Matt, is that possible to put that over there on the switch what's on the big screen? Oh, just switch to have the right screen up here.
Oh, okay. Hi.
Yeah, no worries.
PC main.
Awesome. Thanks.
PC main.
Oh, yeah, it looks good. Appreciate it. So once you're in there, you're going to want to go down to this Git. This may be in a different location depending on what your layout is. Click on Git, and then you're going to want to pool, and that'll update to the new repo with some of the new material for today's session. So, good. People in the room? Great. So basically, you should have, if you go over into files, you're going to have something that looks like this, where it's going to say like workshop. You'll see the one, you'll see a README, you'll see statistics, and there's kind of a blank one for bioinformatics, which will be in about 6 or 7 weeks' time. And we're going to be in the statistics one. So, okay. So, if that has worked for everyone, if you go into the Workshop 2 statistics, you go into lectures, you should see 2 files in there. What's in this folders? Okay, there's something, folders. So you should see a day 1 intro testing R Markdown and a day 1 intro testing HTML. We're going to be working on this day 1 intro testing R Markdown. So we're going to click on that. I'm gonna, let me see, quick. Okay, that's, yeah. Okay. So, click on that, and that's gonna load up what we're gonna be working on today, going over some basic concepts and whatnot. So, does anyone not have this? All right. So, part 2, day 1. So if we're all good, we all have this 01 day 1 intro testing R Markdown here. This is what we're going to be working on. So, this is going to be Workshop Series 2. So today, we're going to be going over quite a bit of material. I think the plan is to have, a lot of the sessions are going to be 2 hours. Today, maybe 3 hours due to just a lot of material that needs to go through, but we'll see how we can do. And we're gonna we'll probably have a break around 2, for people to get up and stretch. And then, we'll, come back and we'll have another break around 3 and go from there. All right. So Lauren Howard posted a link to a sign-in sheet on the chat, so I'm going to run it real quick. For people in the room, we'll get to it. I'll get, or I guess actually you'll have the link, so you can just click on this right here. Click on that link, find your name, and just put an X by it. If your name isn't listed there, just add it to the bottom. We had a lot of people signing up kind of for a while, and that's completely fine. So, and this is just really useful for us since this is a NIAID grant. We have to kind of report on stuff, so we just like to take attendance. So, first off, and I get the 2 people in the room, I also got you. We're first off going to load our environments for today. So we're just going to run this code chunk real quick. So this is going to load a bunch of packages that we're going to be using and set up kind of the path to some of where the data is going to be. So I'm just going to run this. So to just run this code chunk, I'm just going to press this green arrow over here, and that's just going to run it for me. So now I have all the libraries loaded and these kind of paths that'll be useful for when we're loading in data. Okay. So sign-in sheet, have that, and then people in the room, you want to scan a giant QR code. 2 giant QR code is too big. You can do that to also get to the sign-in sheet. So, introduction, as I said, this is this R25 from the NIAID on quantitative methods for HIV research. This is the second in a series. So the first series was kind of going over coding and a little bit of information in the back half about, say, some summary statistics like means, modes, and what have you. And this next one is statistics. And something new we're doing this year is we're going to have a kind of, the last day was typically a bring your own work and kind of talk to people, you know, kind of walk through some code or whatnot, or walk through a case example. But this year we're going to try something new. So we're going to try this day 6 kind of a like design studio setting. So basically, if you're interested in that, you can come and present and kind of talk about your work and whatnot and get feedback from both the people that are attending. So hopefully everyone can attend. And then also from some of the professors that are involved in the org. So just keep that in your mind. We're going to open up a sign-up sheet kind of halfway through. We're going to try to have like 5 people, if 5 sign-up spots. And the idea is to kind of just an open discussion about maybe work you're having or problems you're running into. So each person will have about 30 minutes. They should be talking about a current project that they have related to kind of, for this case, related to statistics. If, say, we do this in the, you know, one of the other series like bioinformatics, it may be a bioinformatics problem, and it's kind of high-level issues. No IRB data should be presented or anything like PHI. And then, you know, if you're doing slides, no more than 20. So if you're interested in that, feel free to email me or Kelly, and, you know, we can give more information. It's kind of a new thing. We're not going to, we may record it, but it won't be posted to YouTube. As people are aware, we, you know, we're kind of doing a lot of these where we put them up to YouTube for people to watch later. This one, you know, we may record if people are interested in it, if they want to go back and watch the notes, but the idea is this won't be posted to YouTube. So just keep it in your mind if it's something you're interested in. All right. Any questions on that? No. All right. Well, let's jump right in then to the data examples we'll be using. So we have 2 case studies we're going to be using. The first one is this case study from this efficacy trial of a RAD5 vaccine. So if you're interested, the link to the New England Journal of Medicine paper is here. So this was a paper from, let me see, when was it published? In 2013. And, you know, we've downloaded the data from this public data source, SHARP, which is a group out at the Seattle at the Fred Hutchinson Cancer Research Center that kind of oversees AIDS vaccine trials. And we're going to be reading in a secondary data set from this larger trial where they collected a lot of immune markers. So they collected all this antibody information in between the placebo and the vaccine treated groups. And we're going to be looking at that and kind of using it as something to kind of play around with. All right. So we're going to read that in. So we're going to read in the larger data set. So we're going to read .csv. We're going to specify the path, read that in. So we can highlight this, and then if you press Control Enter, it should run it. So now I have this case 1 loaded in my environment, which is a 2,504 by 27 matrix or data frame with all this information about the study participants in this trial, right? They also have information on risk factors associated with each person, whether or not, you know, based on, so I should apologize. Apparently, we're trying not to use the word risk anymore and using these terms, but activities that may involve like an increase in HIV transmission. So we're going to be reading in this additional data. So if we look at this, so this dictionary risk, which I'll show in a little bit. So we're reading in this Excel file, and we're reading in this sheet in particular. And then we're reading in the actual data itself. And then we can look at what the dictionary says for what these risk factors are. So I take this data frame, I pass it to this function cable, KBL, and then, I give it a kind of a nicer form, and this tells us what's in here. So we have in this data set, we have the publication ID, we have what treatment they're in, we have what treatment arm, right, which is the same as this. We have this information on other cohorts that may be involved, and then we have kind of, say, more information about individual kind of risk factors, so maybe number of male partners, HIV positive male partner, unprotected insertive anal sex, female partners, transgender partners, exchange of sex for money or gifts, and so on, right? So they collected a lot of information about these people. And then we can look at what the actual data set looks like. So we're just going to look at the first 5 rows. So this head function is just going to give the first 5 rows of this DF case 1 risk, which is the actual individual level data. So otherwise we get this too much information, right? So you can see it kind of has publication ID, right? Publication ID, treatment, MITT, then all these other additional ones. So we're going to just look at the top of this, and then I'm passing it to this function called data table, which kind of gives it in a nicer form where I can kind of scroll and look at everything. Okay. And now we're going to join this risk factor data frame back in with that larger data set of 2,500. Actually, so these both are the same size. So if we look at this. So this is 2,500 individuals. This is 2,500 individuals. They just have slightly different variables between the data frames. So we're joining those risk factors into the case 1 data frame. So we'll do case 1, left join to DF case 1 risk. It tells us it's joining by these variables, treatment, publication ID, and treatment, TRT, right? So that's the common ones it's using to join them together. And now if we look at the dimension of case 1, it has, 20 more columns because originally, we've added all those risk factors to it. Any questions on that so far? It's kind of preliminary. All right. So, as I mentioned, we're going to be looking at this additional data set from James et al., which is looking at T-cell response. So I have some information here about how they enrolled people. So you can see the larger study and then how they broke it down to include, get down to the 100 or 200 some people we're going to be looking at in this with antibody data. And I've given the links to the 2 papers there. So now we're going to read this data, HV and T-cell and BAMA data. So BAMA is binding antibody multiplex assay. Is that right? Did I get that right? Anybody in the chat? No? No?
That's right.
Sounds right. Sounds scientific. So yeah, it's a measure to antibodies against various antigens, right? So you're producing IgG, against HIV, right? So we'll read that in. So this DF case 1 immune data set, and so this is going to be, as I said, a subset. So it's only 189 people, and then it's going to have 105 additional columns. Right. And we can take a look at this, and we can see we have all this information like CD4 response to any DRC envelope, or CD4 response, or CD4 CMV interferon gamma response, and so on and so on. Okay. All right, so that's case study 1. So next off, we're going to talk about the second case study is looking at the superiority of viral load over CD4 cell count when predicting mortality in HIV patients on therapy. I've given the link to this paper here. So this is an additional paper where we have we're going to be looking at viral load being less than 50, so adherence, and the whether or not viral load being less than 50 and adherence to their medication, right? So whether or not they're actually adhering. So read that in. So this is going to be case 2. I'm going to mutate and add this kind of log 10 viral load variable. So the viral load is kind of on the kind of raw count. And, typically we like to have things on the log scale, and then we're going to have this variable for whether or not it's undetected, right? Which in this case is less than or equal to 50. So once we do that, we can see we have this information here about their treatment. So we have the ID, and then the adherence, their gender, their age. And so this was every quarter. They're following up with these people. It looks like the viral load, their weight, kind of what medication they were on, information about mortality, and whether or not there was any kind of control. All right. So there's one person that had a recording of 0 CD4s, so no CD4s in their body. We're going to drop that person for the sake of this study because that doesn't necessarily, I don't know how to make sense of that. So that person will be excluded for the example of this teaching exercise. All right. And then this is just some additional kind of backup that we're going to be doing, looking at viral control. So I'm just going to run this, but the idea is we're just going to get kind of whether or not they're actually virally controlling over the period. So for the sake of time, I'm going to kind of run through this kind of quickly, but the general idea is we're going to reduce to each person to a single observation about whether or not they controlled over the follow-up period and whether or not they were adhering to their medicine. So if you want the kind of QC stuff, you can dig into a little later, but for the sake of time, I'm going to move on. Okay. So any questions on kind of that preliminary, getting the data up and running? Awesome. So now let's talk about hypotheses. So I'm going to give some brief definitions of the difference between, say, a research hypothesis and a statistical hypothesis. So a research hypothesis is some kind of statement about some answer to a research question, right? A statistical hypothesis kind of formates that research hypothesis into some kind of parameters of a population. So the mean, the median, the proportion, the odds, and what so not, right? So we're kind of dialing it down into some kind of mathematical term that we can then test. So in case 1, it may be, are those people that have had an HIV positive male partner older than those that have not, right? That's a research hypothesis. Research question. So then our research question. Then our research hypothesis is there is a difference in the age between those who have had an HIV positive male partner and those who have not. And then our statistical hypothesis is written out using Greek letters sometimes or whatnot. So here it may be H naught is mu1 is equal to mu naught. The alternative is that they are not equal, and then we say where mu1 is the population mean age among individuals who have had an HIV positive male partner, and mu naught is those that have not, right? So we're kind of writing it down into something where now we can estimate mu1, right? And we can estimate mu naught. And then it's kind of a similar process through like case 2, right? So if we say like the proportion of individuals with undetectable viral load over the follow-up time will be different among adherers than among non-adherers. And then we may write pi of adherence is equal to pi of non versus our alternative, where these are kind of the population proportions of individuals with virological control, which here we define as a viral load less than 50, less than or equal to 50. And then they correspond to the adherers versus the non-adherers. Okay. So the H naught typically denotes the null hypothesis, and then HA is what people typically use as the alternative. These need to be mutually exclusive and exhaustive, right? So you can't have overlap between the two. And then it's kind of either or, right? Either one is true, the other is not. You can't have both. The null is typically kind of the status quo, the more conservative thing that we're trying to maybe prove against. So, in the US legal system, H0 would be like the defendant is innocent. So in drug safety studies, it may be H0 is the drug is toxic, right? Well, the alternative is you have to prove that it's safe. Efficacy studies, it may be the drug is not efficacious versus the alternative is the drug is efficacious, right? And that may be with reference to some existing drug that's in the market at the time. And then once we have that, we then construct some test statistic, and then we make a statement about whether or not we reject the null hypothesis and that we have evidence with respect to the alternative. So we're making a decision about whether or not we think we can reject the null and we have evidence to support the alternative, or we can't reject the null. All right. Any questions on that? Okay. So, as I said, we're doing this decision. So this leads into these two terms that maybe people have heard called the type 1 and type 2 error. So due to the randomness of the data, there's potential errors that could be made, right? So if the row is whether or not the null hypothesis is true, is the top row, and the alternative is that, the bottom row is that the alternative is true, and then we see our decision, we can have what's called a type 1 error or a type 2 error. So a type 1 error is where you reject the null when actually the null is true, right? So you say, declare that the drug is not toxic when in fact it is toxic, right? A type 2 error is when you fail to reject the null, but the alternative is true, right? So we're typically more concerned about the type 1 error, right? We want to control the type 1 error. So that's why I'm going to say you have, this leads into that p-values, right, that eventually we're going to get to. So you'll see in kind of statistics textbooks, they'll usually then let alpha be the probability of type 1 error, and then beta be the probability of a type 2 error. And then typically they have 1 minus beta denoting the power, like how powerful is your test going to be. So typically we worry about controlling the type 1 error. So that's why you may see like 0.05 is commonly used. So that's what we're trying to control for, is not rejecting the null. Rejecting the null when the alternative is true, we want to avoid at all costs. Try to avoid, all right? So, and there's always going to be a trade-off between these two. So you can't often increase alpha and beta at the same time. We typically then, control alpha, usually 0.05, which was not decided, just somehow came into consensus. And that's something that needs to be kind of decided before you actually do any tests, right? So if you're doing a purely explorative analysis, right, and you're just hypothesis generating, maybe you want to increase that, right, if you know that you're going to be doing more studies later on. Or if you're doing multiple studies, you may want to make that alpha more stringent. So maybe you want to do 0.01, right? Because the more often you do a test, the more likely, potentially purely by chance, that you may reject the null by accident, right? So a type 1 error in that drug efficacy study would be that you conclude that the drug is efficacious when it's not. While a type 2 error would be that you conclude that the drug is not efficacious when it is, right? Okay. So, let's talk about rejection and no rejection. So when we reject the null, we're saying that we have enough evidence to reject the null. So the probability of observing what we did, if we're actually in the null space, right, if their means are equal or if the drug is efficacious, is less than this alpha that I set. It's less than 0.05. So it's a small probability we would observe that if the null is actually true. So we say, okay, let's reject it. No rejection just means that you don't have enough evidence to reject the null at that current alpha level, at 0.05. It doesn't mean you have enough evidence to suggest that it's true. It just means you can't reject it. Okay. And then there's some additional information there about, it's hard to kind of do power. You can't do like post hoc power analyses because, the test has been done. And remember, you always set the alpha prior to the study. Any questions about that before I move on into test statistic? Any questions on Zoom? No? Okay. All right, so test statistic. So a test statistic is going to be a way to compile all this information into a number, a single number, that we can then come up with some decision about the hypotheses. So there's always going to be multiple test statistics to answer every question, right? So there may be something like a z-test or a likelihood ratio test or a score test or a wall test, and you'll hear all these terms, right, that are all getting at the same thing. And, typically what it is some are more powerful under certain circumstances. Some have certain assumptions that are necessary to be met that others maybe don't. So there may be a test that doesn't require as much assumptions, but it's not as powerful. So there's always going to be this kind of trade-off, right? And there's always statistical papers coming out where people are like, I found the new most powerful test for testing in this scenario, right? The t-test stuff is pretty settled by this point. So a test statistic is going to be a random number because it's a combination of a bunch of random variables from our data set. And we need to know the distribution of that test statistic to make some decision on the alternative. So there's a couple ways people do this. The kind of older classical is what's called an acceptance region, where it's the range in which the statistic fell in that range. It's larger than 1 minus alpha under the alternative. So it's like an area where you would accept, you fail to reject the null hypothesis. When it's outside of that, you maybe reject. So I think before, computers were pretty commonplace, right? Acceptance regions were more commonly used because every textbook, if you've ever seen an old stat textbook, has like these p-value probabilities in the back at the end of the book. So a p-value then is going to be the probability of observing a test statistic more extreme than what you currently have if the null is true. And that more extreme is always defined with in response to the alternative. So if our alternative is said that they're not equal, it means observing an absolute value of, say, a test statistic that is larger than what you currently observed. If it's that it's less than, say, so this is a typo. This should be actually, let me put this in. So if you recall what I said earlier, I said they have to be mutually exclusive, right? So originally it was just mu is equal to 0, but it didn't have the greater than part. So now it's saying the null is that mu is greater than or equal to 0. The alternative is that it's less than 0. And then I did this similar for the other one. So this p-value is also a test statistic. It has a random distribution. And then typically under the null, it follows what's called a uniform distribution between 0 and 1. So p-value will be smaller when the observed data is more in the direction of the alternative, compared to what is expected under the null. So we typically reject the null when that p-value is, sufficiently small at the alpha level that we've set a priori. So at like 0.05 or whatnot. Okay. All right, so we talked about type 1 error. So the hypothesis testing steps. So we got to know the data. So you need to know the type of data, the study design, and the distributional assumptions, right? And we'll go into that for some examples. So we're going to go over it over your classic one sample hypothesis testing. You have to set up the statistical hypothesis and choose a significance level. Choose a test statistic that we're going to be using to test it. Then you actually calculate that test statistic and maybe compute a p-value, and then you draw inference based on that significance level. So at least in my head, when I like to think of inference, I like to think of we're talking about an alternative and a null and an alternative hypothesis, and we're making some decision, right? Which is different than prediction, which we'll get to later, which is more about just how well is this doing in predicting the actual y. I don't necessarily, care about a p-value. I just want to know, can it predict that? And that's a different set of tools to evaluate. Okay. Any questions on that before we go into this one sample hypothesis testing? Yeah.
You said that a question was.
Oh, it's okay. If it comes back, just let me know. All right. So one sample hypothesis testing. So now we're going to be talking about testing for, say, a population mean, like mu. So we want to know whether or not some value, what we observe is different than some pre-proposed hypothesis, right? Some pre-proposed value. So we're going to be looking at this antibody data. And so I may come up with a better example for this in next year. But we're going to be looking at whether or not the CD4 response of this TNF alpha, the cytokine, to the CMV virus is different than 1%. Okay? So any biology, I'm forgetting exactly what TNF alpha does. Does anyone have a good answer that they can put in the chat, or if they know in the room? No? Okay. So in this study, right, so this was an HIV study, right? But they also wanted to see how well people were responding to maybe other viruses that are common, that are maybe more common. So CMV is a relatively common herpes type virus, cytomegalovirus. So they also measured the response to that in this group, in this subsample of 189 people. Okay. So we're going to be loading back in some of the original data. So there's some, this is kind of a data table of what's in this file I'm about to read in. So we're going to be looking at this % positive value. So this is the net % of cells positive for TNF alpha when stimulated with CMV. So we're looking at how many of their cells were expressing TNF alpha, their CD4 cells, when exposed to CMV versus when they're not exposed to CMV, right? Okay, so we're going to briefly read in this data. So I'm just going to run this really quick, since just due to time. But hopefully there's enough comments there. So if you wanted to follow along piece by piece, it should be relatively straightforward. So we're basically going to have this data set now, where we have a publication ID, and then we have this information on the % positive of CD4, CMV, TNF alpha. Okay. So this is kind of, it's pretty low. So this is only 3%. This person, only 3% of their cells are expressing this, of their CD4 cells. Okay. All right. So first, let's look at the distribution of this CD4 positive cell. All right. So we see the minimum value observed is 0. the median value is 0.09, the mean is 0.5, the max observed is 6%, and the standard deviation is 0.94. And we have 189 people with this data. Okay. So then we can make some plots. So we're going to look at first a histogram of this value. We're going to look at a density plot. And then we're going to look at a box plot and then a violin plot with a box plot overlaid. So I'm going to run that. So there's a couple ways we can do this. We can press this button up here, which says run current chunk. Here's this chunk. Or if you have a Windows machine, it's Control-Shift-Enter. We'll just run that whole chunk also. And I think for Apple, it's whatever the Apple equivalent of control is. So we can see what this data looks like. So you can see it's pretty skewed. Looks like there's a lot of density values here, right, at the bottom. And then, you know, what kind of the box plot and the violin plot is. So you can see there's a ton of data here way at the bottom. So how the study was designed will always influence the test that we're doing. So here we're going to be doing something called a t-test for whether or not this value is different than 1%. Okay. So the assumptions here is that the data is approximately normal. Clearly, this data is not normally distributed, right? So normally distributed is like bell-shaped, right? So we're going to graph it. So what we're going to do is look at these QQ plots, right? Which are basically taking your data and comparing them to a normal or to whatever distribution you may have. So we're going to look at it and see how well it looks. So I'm going to run this. So this is you want your dots to fall along the red line, right? So this isn't happening, right? And clearly there's a mass here at 0, which suggests like a lower limit of detection problem or something along those lines. So in the real world, if this occurred, you may want to consider a non-parametric test, which we'll talk about a little bit later, hopefully, or you'll want to kind of consider other testing methods that allow for data to be, say, 0 and the rest of the data to be continuous. So there's things called hurdle models or Tobit models, which are kind of beyond the scope of this class, this workshop. But in general, there's always some method that has been developed to deal with probably what you're observing in the data. So this is the kind of raw percentages. And then if we look at it, say on the log 10, it's like a little bit better, but still not really great. So the data isn't normal, but for the sake of an educational experience, we're going to pretend like it is and kind of pass along to this t-test. All right. So the null hypothesis is, the null hypothesis is that the CD4 TNF-alpha response to CMD is 1%. So statistically, H0 is mu is equal to 1%, where mu is the population mean CD4 TNF positive response. That should be 1. And then the CD4, the alternative is that the CD4 TNF response is different than 1%. And then the alternative, writing it out mathematically, is that mu is different than 1. All right. And we're going to use alpha equal to 0.05. So just what do people think, given what the mean and median is? Do you think that this is going to be different than 1%? Don't bias yourself now.
I think yes.
You say yes? Okay.
I'm saying yes.
All right. So, you're going to say, yeah, perfect. We got a perfect split. So, great. So, we're going to go on down and we're going to calculate this to test statistics. So we're going to be calculating what's called a t-test. We're going to be doing, it's called like a student's t-test, which was created by I don't know his actual name, but he worked at the Guinness factory when he came up with it. So if you go to the Guinness factory in Dublin, there's like a plaque that says the t-test was created here in like one little small corner. And usually if you see someone taking a picture in front of it, you know they're involved in academia probably in some way, because those are the only people that are going to know what that is. It's like if you go to the London and go to where the pump is from like John Snow for like the cholera epidemic. You're like, that's a public health person there and taking a picture of that. Okay, so the test statistic has a kind of set form. So where it's the mean that you observe in your sample minus your null divided by your standard deviation estimate divided by the square root of n. So this is kind of the form of the test statistic. And under the null hypothesis, this is going to follow a t-distribution with n-1 degrees of freedom, right? And so in our case, it's going to follow 180. Now I'm going to give this, but you know, typically we're going to just do this in R kind of quickly, but just reminder, these all have like closed forms, a lot of these tests, and you know, they have been calculated and figured out. So there is just this kind of math going on in the background that is going to be kind of easy to figure out. So we're going to look at the critical values. So basic run this. So if we get a test statistic that's in the white area, so it's not in the red, that means we're going to reject our null hypothesis, right? Because if it's within here, the probability that we would observe it under the null is like, you know, greater than 95%. All right. So if we wanted to calculate it, we would calculate the mean, the standard deviation, and then we would calculate the test statistic, plugging that in. So I'll run this really quick. This gives the summary again. And this will give us our test statistic of negative 7.29, right? So that's outside the rejection region. So if we wanted the p-value, we would calculate the probability that we observe a t less than or equal to negative 7.3, plus the probability that you observe something greater than or equal to 7.3, which would give us a very small p-value, less than 0.05. Okay. So we would reject the null hypothesis that the CD4 TNF alpha response to CMV is 1%. We have sufficient evidence at the 0.05 level to suggest that it is different than 1%. Based on our data, it appears to be less. Now, granted, this is all with context of this population, right? So we'd have to probably add some caveats about this is within this group. But for just kind of the sake of calculating, this is kind of how you do it. And we could look at the critical values and also calculate, you know, a confidence interval. So you were 95% confidence that the mean value is between 0.364 and 0.635. Right. So if we wanted to do this in R, right, which is what we'd typically be doing, we wouldn't be calculating this by hand. There's a function called t.test, where you give it x, you give your alternative, you give what your mu naught is, and then there's some additional information which we'll use later on. So we pass in our variable of interest, we say our alternative is two-sided, we say our mu is equal to 1%, and then we run this. So if I run this, we see a negative 7.2931, which is what we got before. We see our p-value of 8.202 times 10 to the negative 12. We can see our confidence intervals, and we see that gives us our alternative hypothesis, right? So if, say, we thought that it was less than 1%, so let's see, if we did this and put less, what the, do I have insert? No. Oh, sorry, something's alternative equals. Sorry, something weird's going on with the right, it's not going to reject in that case because it is less than 1%. Right.
Yeah.
So the alternative is like that. No, we don't have evidence to suggest that it's less. You know, you can't reject the alternative. Okay. All right. So I want to briefly say I misspoke on that last example. So really quick, I'm going to go over that. So when I ran this x equals variable of interest alternative less, so this t-test automatically assumes the mu is 0. Okay. So what this is actually doing is saying, all right, the null is that mu is greater than or equal to 0. The alternative is that it's less than 0. So that comes back as not significant, right? If we actually had it this way, which is that the null is that mu is greater than or equal to 1, and the alternative is that it's less than 1. This comes back as highly significant, right? Because the mu is actually very much less than 1. Finally, if we had it the other way, where say the null is that mu is less than or equal to 1, and the alternative is that mu is greater than 1, right? So in this case, it comes back as non-significant, right? So I forgot to include here basically the mu equals 1, and I got my order slightly mixed up in my head. So always, important to me, but I just wanted to give that correction. Okay. All right. So let's talk about paired tests. So paired tests are when we have data coming from the same individual, right? And we want to know whether or not they're different. They're same individual or same cluster, right? It may be like parent and child or something along those lines. And we want to know whether or not they're different. So here we want to know whether or not the CD4 and CD8 response to CMB TNF alpha is different. Okay. So we're going to calculate this new change variable, which is going to be the difference of the two. Right? So I'm going to take this data frame that has all this information. I'm going to calculate the difference. And then I'm going to pull out that new variable, new change. So if I run that, we now have this variable here where you can see, okay, so this is a place where there's more CD4. This is a place where there's more CD8. This is a place where they're equal. This is a place where there's more CD8, and so on, right? So we have this just as a vector. And now this test statistic is basically the same as the one sample t-test that we calculated before. So we can calculate it and then calculate the probability. You get 2.72. And then in R, the way you would do it is you say X equals that variable change. You say the alternative is two-sided. Your null is that they're equal to each other. And then for this, we say paired equals false. So if we run that, it gives us the test statistic and the resulting p-value about whether or not, and the alternative is the true mean is not equal to 0. So here, it's basically that the null hypothesis, we reject the null hypothesis that they're the same. We have evidence to suggest at the 0.05 level that the mean response of CD4 and CD8 from the same individual is different. Okay. Another way you can do this is pass in an X and a Y. So if I say put CD4 TNF alpha as this variable, and then CD8 as this variable, and then I say X equals this, Y equals this, I give the alternative, and then I say paired equals true. So I say, hey, these are from the same person. Right? If I run that, oh, I also got to run the top part. I said, oh, okay, we're now doing a paired t-test. But you can see it gives, you know, the same kind of values, same inference. So I'll run these all at once. So you can see the similarity. So they're giving the same values. Okay. Now, if the data is not from a normal, which this data wasn't, but we pretended like it was. Typically, you know, if you have a large enough sample size, there's, you know, this thing called the central limit theorem, which says that your mean should converge to a normal, right? So you should be okay. There's also something called the Slutsky's theorem, which kind of allows the normality assumption. So that resulting test will be approximate. You know, it'll be more accurate as your n gets larger. There's all these rules of thumb, which I'll just leave here about how large is large enough. But yeah, it's you kind of always have to look at it and figure it out. If these don't hold, then there's always tests that are maybe specific to that type of data. So if it's count data, there may be things like Poisson or something along those lines you may hear of. Or you may be able to do an exact binomial test, or there may be all these other, you know, exact tests or non-parametric tests. So there's always a lot of different ways to do it. So we're going to now switch to case 2 and perform a test of the proportion there of HIV follow-up. So we're going to see whether or not at the 0.05 level, this suggests whether or not the population proportion of people who control HIV is different than 50%. So we have 140 individuals, 47 of them have virological control. So in this data, this is a binary variable where 1 is control and 0 is failure. And the idea is each of them follows what's called a Bernoulli, which is like a coin flip, basically with some probability. And, you know, we can perform basically a z-test for whether or not this is different than 0.5. So we're going to get this VCFUP, virological control follow-up, and then we're going to get a table to see what it looks like. So we can see we have 93 people who didn't control, 47 that did, and then that's basically 66% of them didn't control and about 34% did. All right. So, and we want to know basically whether or not that's statistically different than 50%. So the rule of thumb, right, is that if this is greater than, if n times your pi naught times 1 minus pi naught is greater than 5. So if 140 times 0.5 times 0.5 is greater than 5, we should be okay. It's 35, we should be all right to do this. So what this test is going to look like is going to be very similar to the kind of t-test we saw, but basically you take the p hat, which is the mean probability in our sample, we subtract the null, and then we divide by the estimate of its standard deviation. Okay. And then with sufficiently large data, and because of all these theorems, this should follow a normal with mean 0 and standard deviation 1 under the null hypothesis with sufficiently large n. Okay. So we can calculate this by hand. if you wanted to. If we wanted to do it in R, like setup, we go sum, we get the average, get our pi naught, we get our length, construct our test statistic, construct our confidence interval. So just to walk through this case, so what we're doing here is we're taking estimating our mean proportion in this sample. So as a reminder, BC up is basically a bunch of zeros and ones, right? So we're summing this up. 47, and then we're dividing by the length. So this is giving us our n. So we do this, and we divide by the length of VC FUP. We get 33%. We have our pi naught. So this is going to be the numerator. This p hat minus pi naught. Right here. And then we're dividing by the standard deviation estimate, which is pi 0 times 1 minus pi 0 divided by it, right? So if we calculate that, we'll get a value of negative 3.88. So if we wanted to calculate a p-value, so I'm going to add something here. I'm going to switch back to source real quick. It was annoying me. All right. Where were we? Okay. Yes, here we are. All right, cool. So I'm gonna basically absolute value of C, go over to false. That's going to give us a p-value of 0.001. So we're going to have evidence to reject the null that it's 50%. So if we wanted to do this in R, there's something called a binomial test, where basically you pass in the number of successes you observed, successes here being the controlled. And then you basically give it the length, you give it your alternative, your null, I mean, and you tell it its alternative. So if we do that, we get this value here, we get 0.000. So this is an exact binomial test. So this is using the fact that the data is from a Bernoulli and calculating the test statistic that way. And then if we wanted to do the kind of the normal approximation, we'd use this prop test. So you can see it comes out to that 0.10, kind of which is what we got earlier with the approximation. So you can see like they are different up to like the 5th decimal, you know, they differ a bit. But in general, once you kind of have a large sample size, you're going to get very similar results. Any questions on that? Any questions on the Zoom? Okay. Well, I'll go on then. So step 5, we reject the null hypothesis. Okay. The most important step, according to journals and folks. Okay. So 2 sample hypothesis. So now let's say we have observations from 2 different groups, and we want to do a test for whether or not they're different. So we have like say 50 people from one group, 60 people from another group, and we want to test whether or not some continuous measure is different between the 2. Excuse me, age or IgG4 or whatever. So I'm going to switch back to visual mode. So it looks a little nicer. So it loads. Okay, so there we go. All right. So population 1 has some mean with value mu1, some variance sigma squared. And then population 2 also comes from a normal, let's say with mean mu2 and some standard deviation. So here, we're first going to start with, say, assuming that they have equal variance. Okay? So we're assuming that the unknown variance of these two populations is the same for this measure of interest. We'll talk about what to do when they're different. Like, how do we do that then? So we want to estimate the means between these two groups. We're going to assume the variances are the same. And of interest is looking at the difference between the two population means and assessing, whether or not, typically, right, we assume that we expect that this delta here, which is mu1 minus mu2 is 0, is typically the null hypothesis, right? But sometimes it's maybe that one's greater than the other, or maybe you think the difference is 10. It all depends on the context. So this difference is, if everything is normal, is also going to be normal. So if we're interested in, let's say, D, which is defined as y1 bar minus y2 bar, that's going to follow a normal with difference mu1 minus mu2 with variance sigma squared divided by n1 plus sigma squared divided by n2. Okay? And so from that, we can kind of construct a test statistic, which is what we're going to do. So one issue that comes up that we first have to deal with is estimating sigma squared, right? Because we have to use that, we have to come up with some estimate of the variance to draw inference about the test statistic, right? So if the data is like hugely variable, right, then maybe that kind of leads to a smaller test statistic. So what people typically do is they add what's called a pooled estimate, where they basically take the estimate in the one group and then add it to the estimate in the other group and then divide by basically the total n minus 2. Okay? And this will give an unbiased estimate of that unknown population variance if everything is, copacetic. So from that, we can construct a confidence interval, which is, say, going to be y1 bar minus y2 bar, plus or minus some critical value divided by the square root of the pooled variance estimate, right? And then the number of degrees of freedom is going to be n1 plus n2 minus 2. Okay, so let's do an example. We're going to be looking at this IgG GP41 value. So this is looking at the antibody response to GP41, which is a peptide of the HIV envelope. So like part of the HIV virus, I think it's a protein. If I'm wrong, please correct me. Or if it sounds good enough, it's fine. So we're going to basically look at this amongst the people that received the vaccine, right? We're going to look at whether or not this value is different based on that risk behavior of unprotected receptive anal sex. So we're basically, our two groups are going to be the one group that has had unprotected anal sex, receptive anal sex, and the other group is ones that have not, right? So group 1 and group 2, and then we're going to basically construct and draw some inference on the difference in the IgG GP41 between these two groups. All right. So we're going to take our data set. We're going to select this publication ID and the data that we're interested in. So what this is going to do right here is basically just give us, two columns with the information we want. So their publication ID and then this IgG GP41 value. We're going to join it with that risk data frame, if you remember from earlier at the start of this class. So if we do that, we now have, those two columns, and then we have this additional information about treatment and all those risk factors that they define. All right, and so we're just going to look in the vaccine group, and so we're going to filter this to just the people with the vaccine in this, because there's a little bit of individuals that didn't receive the placebo in this group. I believe that received the placebo. I believe it's small. Let's see. Because I believe the idea is, so let's see, I'm going to say count, treat. Right, so if I recall correctly, the 39 that received the placebo may be people who actually then became infected or acquired HIV. And I believe that, the idea is like, well, if you got the vaccine, if you got placebo and you weren't exposed to HIV at any point, right, either through the vaccine or through behavior, you wouldn't necessarily expect an immune response to HIV unless you had already been exposed somehow. So we're going to just filter to the vaccine folks. So that's going to give us a data frame of 150 individuals. All right. So we can then look at the distribution of this IgG GP41 between the two groups. So we're first going to look at the density in the group, we'll call them group 0, which is the group that hasn't had it, the exposure. And we're going to add kind of some information about their QQ plots and whatnot and see if it looks relatively normal. So we can look at the distribution. Looks pretty good. We look at the QQ plots, compare that to earlier. This looks fantastic, right? It looks pretty normal. And we can then do the same in the not engaged. So you can see this is basically the same code as above, except instead of saying equals 0, I'm now saying equals 1, right? Because we're now looking in that group of people who have received unprotected receptive anal sex. So we look at that, and it looks pretty good. So we're maybe a little off, but for the sake, we're going to go ahead and assume that they're normal, right? Okay. So we can compute the pooled variance. This is kind of how you would basically calculate it if you wanted to by hand or, using R. So that's going to give us an estimate of 2.66. And then if we wanted to, we could say the 90% confidence interval, the 95% confidence interval, and like the 99% confidence interval. And what you can see is as you're kind of increasing the confidence, right, they're getting wider and wider. So 90% confident that the true mean difference is between negative 0.16 and 0.72. 95% that is between negative 0.24 and 0.81. 99% confident that it's negative 0.41 to 0.98. So you can see it's kind of getting larger and larger windows, right? Because getting more and more confident. It's like me saying, I'm 99% confident Venice, Florida is in Florida. Wait, so let me try this again. I'm 99% on Venice, Florida. I'm like 90%. Now, that's a bad example. I'm going to cut this out, actually. Yeah, so there's, we're just kind of increasing the window as we get more and more confident. I backed out of that example because it's either on the Gulf Coast or it's on the Atlantic Coast. There's not like 0, 1. So, all right. So hypothesis testing. So we have the two populations. So we have here it's it's not treatment. It's this risk factor, and we're going to look at whether or not they are different. And another big assumption, right, is that everyone's independent of each other, right? So hopefully people don't know each other, right? So this was a nationwide vaccine trial, so we're probably okay. That there's not maybe people from the same household or things along those lines. And we conduct our test statistic, and it would come out to 1.054 if we plugged it into this formula. And then that would give us a p-value of 0.293. Okay. Now I'm going to go over how to do this in R with like their t-test function in a little bit. Okay. So if you weren't comfortable assuming that the variances were equal, there is what's called an unequal variance test, where basically instead of having that pooled estimate, you have the actual individual observed in each group. So S1 squared and S2 squared divided by distributed N1. So you can look at kind of compare. So if you assume equal variance, right, you have the pooled variance estimate there. If you assume unequal, you have their individual ones. So the catch with this is now the degrees of freedom aren't clear, like what actually this follows. So there's a researcher, Satterthwaite, who came up with this kind of approximation for what the degrees of freedom would be in this formula where this VI has this form, and this is, will be kind of an unknown, will be an estimate of the degrees of freedom. So this is what we will use instead when we say calculate the p-value. This will be kind of the degrees of freedom of the t distribution. So in our case, it's 147.96. So if you remember, we had 150 people, right? The regular degrees of freedom, if we assume equal variance, is 150 minus 2, so 148. So they're really pretty close to each other, which maybe you see with larger n. Or when, here the sample variances are actually pretty close to each other. So 2.69 versus 2.63 in one group. So, so if we wanted to calculate that this way, and then we would recalculate the test statistic and then the resulting p-value. So how do we do this in R? We use that t-test function again. And so it has these, we pass an x, which is, say, the observation for population 1. Send y with the population 2. Give our alternative, give our null hypothesis. It's just going to default to 0 if we don't put anything there. And then we're going to say whether or not we think the variance is equal. All right. Alternatively, you can pass in a formula where you say you pass in your y. So this would be IgG GP41. And then you pass in the binary variable that splits them into two groups. Okay. So first off, we'll do the formula. So in this, we pass in this dat.ab data frame, right? And we say, I want you to look at IgG GP41, and I want you to look at, with respect to this this risk factor of unprotected recessive anal sex. Okay? And I want you to assume the variance is equal. So if we run that, it gives us our resulting p-value. It tells us the degrees of freedom, and it gives us the confidence interval of the difference at the 95%. All right. If we wanted to pass it in as a non-formula, you just pass in x and y. So I take that IgG GP41, I filter to where that value equals 0, I filter where that value equals 1. I say the variance is equal. So here I put T, capital T, instead of writing out true. R will shorthand that and know that that corresponds to true. So if we run that, we get the same results, right? Now, if we think that the variance isn't equal, we just change that true to a false, right? And then it'll approximate it. So if we run that, we can see it now is giving that this is, say, the Welch's two-sample t-test. it gives this estimate of the degrees of freedom, 147.96, and the new updated p-value, which in this case is the same because the degrees of freedom are so close to each other, right? So, and then if you wanted to do it the other way, you pass both in, you get the same result. Okay. Any questions on that? And later, I think we're doing pretty good on time. I will show how simple linear regression corresponds to the t-test with variance equal variance. Okay. All right, so when can we safely assume that sigma 1 squared is equal to sigma 1, between the two? So if the ratio of the variance is, say, greater than 3, with the larger in the numerator, you may want to use the formula for unequals variance. Sometimes people use 2. So if they conflict, you may want to, say, use a more conservative test or kind of present both. But this is something you kind of try to decide before actually performing the test about whether or not you actually want to, assumption you want to make. There is a variance test in R for testing whether or not two variances are equal. It's very sensitive to basically the data. So, and remember that it's the null is that they're equal, the alternative is that they're not equal. So just if you don't fail to reject the null, it doesn't mean that the null is true, you just can't reject it. So in our case, we'll look at the variance test. So what this is basically doing is it's testing whether or not the ratio of the two is equal to 1. Right? And so here it comes back as non-significant, right? We don't have evidence to suggest that they're different. And this is based on using a what's called an F statistic. Okay. All right. Next up, we're going to talk about how to do this, the anomalous thing with test of proportions, right? So we're now going to have Bernoulli data, and we're going to say we want to know whether or not two proportions are different between two groups. So population 1 has some pi 1, which is their proportion of whatever the observation is, whatever the binary outcome is. And then population 2 has pi 2. And we want to know whether or not they're different from each other. Kind of similar rules of thumb, where you want basically both of these to be greater than or equal to 5. So n1 times pi 1 times 1 minus pi 1 being greater than or equal to 5, and likewise for n2 times pi 2. And then our point estimate is just going to be the mean difference. So same idea as when we were doing a one sample, that this will follow basically a normal, where with pi 1 minus pi 2, and then variance of pi 1, 1 minus pi 1 divided by n1 plus pi 2, 1 minus pi 2 divided by n2. The confidence interval then is going to be your observed difference plus or minus the critical value for a normal. So z1 minus alpha over 2 based on whatever your confidence interval is going to be, times that respective standard deviation estimate. Right? So what we're going to look at here now in that case 2 is whether or not virological control is different amongst those that are adherent to their medication versus those that are non-adherent to their medication, right? So why isn't that showing up? Oh, weird. Okay. Well, I don't know what's going on there. I'm just gonna let it be. All right, so we have 109 individuals who are adherent at baseline. 45 had biological control over the follow-up. 21 were non-adherent at baseline, and 2 had biological control over the follow-up. All right. So we basically have, this is kind of our table, right? So we have the adherence over here. Notice it's non-adherence. So adherents are coded as 0, non-adherents are coded as 1. There's 2 people that are missing it. And then we have kind of the total in the group. So these 2 people that are missing, I'm removing from the study. All right. And then if we wanted to construct a confidence interval for the difference, we basically take the 2 p-values. So we have, that's not p-values, proportions. So we have 45 divided by 119, 2 divided by 21. Take the difference, we add 1.96 times kind of the respective standard deviation. And that'll give us a confidence interval for the difference of 0.13 to 0.435. All right. So for testing this, we basically first assume that we want to assume that the sample proportions are going to be approximately normal due to sample size. And then we define our alternatives, our null and alternative. So our null here is just going to be that they're equal, right? So for here, the standard error is going to depend on the test statistic that we construct. So I like to think of it as, I like to use the pooled variance, which is going to be the total, using the pooled proportion that have this event, right? Biological control. Because the idea, at least to me, that kind of intuitively makes sense, because if you're assuming that they're equal, then you should probably assume that their variances are equal, right? Because the variance of a Bernoulli is dependent on their mean. So we're going to calculate this pooled proportion, which is basically just the sum of how many outcomes we observed divided by the total. Or it can be written as N1 times P1 plus N2 times P2 divided by the total N. So that'll give us a pool of 0.33. And then our test statistic is just going to be the observed difference divided by this pooled variance, divided by the square root of this pooled variance, this variance estimate. So P1 minus P divided by N1 plus P1 minus P divided by N2. And this should follow a normal under the null hypothesis and the central limit theorem. So we construct that. We get a test statistic of 2.53, giving us a p-value of 0.11. So if we wanted to do this in R, we use that prop test, and now we pass in 2 vectors. So 2 values. So we pass in the observed observation successes in the first group and the total N. We pass the observed successes in the second group and the total group in the second group. And then we have this correction equals false, which corresponds to some additional things in the background, which we don't have to worry about. Oh, there should be a 0 there. Okay, so you can see when we calculated it by hand, we got the 0.11370. And then here, the 2 sample tests for for equality of proportions, it gets the 0.01137, which is what we got. So here it has this chi-squared value. It says x squared because it can't display the Greek letter chi or chi. So this 6.4065 is actually just 2.48 squared. So if we take that ZZ value and we square it, it's equal to 6.0645, which is that value there. So there's a one-to-one relationship between those two. All right. So we would reject the null hypothesis. We have evidence at the 0.05 value that the proportion of biological control amongst those that are adherent is different than those that are non-adherent, which is kind of a no-brainer, maybe. So, yeah. Any questions on that? Any questions on Zoom? Okay. All right. Now, so something that will be maybe talked about in the next class is testing for 3 or more populations, right? So here you move into something called like an ANOVA, where you now have like more than one group. So the null is that the 3 are, like say you have 3 populations, right? 3 groups. The null is that they're all equal to each other. The alternative is at least one of them is not equal to the others. So this typically is done, you have to have the assumption of normality, you have to assume kind of equal variance of the populations, and the test statistic is this ratio that corresponds to an F distribution. And Pishu will talk about this a little bit more next week. It's an extension of kind of the t-test with equal variance. It can be thought of that way. And the t-test is a special case when there's actually only 2 populations of interest of an ANOVA. Right? So let's look at this case 1 data. All right, so we're going to look at the whole 2,500 people, and we're going to look at BMI category by age, right? So we have the BMI category, and we're going to look at whether or not age is, say, different by BMI category. So the way you do this in R, there's multiple different ways. There is a function called one-way.test, which will do it. You can also get at it using linear regression, which will be maybe covered next week. So one-way test of variance, you don't want to assume equal variance. So just you give the y variable, you say, hey, I want this by BMI category, and then you say data equals case 1. Or alternatively, one-way test and go age on the BMI category, data equals case 1, you say variance is equal. True. Right? So these are kind of 2 ways. You see they kind of give you 2 different results, depending on whether or not you want to assume equal variance between the groups. 2 very different results. So let's say we only have 2, right? Let's find the 2 groups. So let's look at age by whether or not they received the vaccine, right? So that shouldn't be associated, right? Because if they did proper randomization, whether or not you got the vaccine shouldn't really be affected by age. So let's do one-way test, age on. Let me look at case 1. We'll do treatment. We'll say equal variance. And then let's do a t-test as well. Okay. So this is the one-way ANOVA, the analysis of means, looking at whether or not age is different than treatment. Right, by age it differs by treatment, right? You can see it's not significant, 0.75, right? Which is what we would expect if they randomized the data properly, which they did, they're very smart. Now, and then we look at the 2-sample t-test, and you can see we get the same p-value, we get 0.75. And actually, if we take this t-statistic here, 0.31863, and we square it, we get that F statistic observed up here. So the t statistic squared follows an F distribution with numerator degrees of freedom 1 and denominator degrees of freedom, whatever the degrees of freedom were. So Pishu will talk about this a bit more next week, but just as a heads up. All right. Any questions on that? All right. Let's take a break now. All right, so let's go ahead and come back. So I am going to talk about some non-parametric tests first. So this should hopefully provide some alternatives, right, if you don't want to make any assumptions about the distributions. So what is a non-parametric test? I'm just going to read this quote from this book by Hollander. So a non-parametric procedure is a statistical procedure that has certain desirable properties that hold under relatively mild assumptions regarding the underlying populations from which the data are obtained, right? So we maybe don't have to assume that the data is normally distributed, which is nice, right? It may make things easier for us. So I'm going to go over a couple different tests, mostly the Wilcoxon sign rank test, the Wilcoxon rank sum test, sometimes called the Mann-Whitney test, and then also the sign test. So the Wilcoxon sign rank test is most analogous to the one sample t-test, right, for testing whether or not something is different. So we're going to go back to that CD4 versus CD8 TNF alpha data. And we want to remember there our null was that it's equal to 0, right? So the way the Wilcoxon sign rank test works is by calculating the rank of the data and then seeing whether or not those ranks are, say, symmetrical about 0. So if they're not, you know, or around whatever your null hypothesis is. So basically, if the hypothesis is true, they should be roughly symmetrical about that median. So the way that the test procedure works is listed out here if you're interested in figuring it out. So, but basically the idea is we remove observations that are equal to the median because they're not going to give us any information. We calculate our remaining sample size. We calculate our rank. And if there's ties, we give them the just basically the average rank. And then we calculate basically this T plus, which is the sum of the ranks times an indicator of whether or not the difference is, say, greater than 0. So are they above or below 0? And so this should be, I believe, absolute value right there. It's xi minus n. So once we do that, we can kind of calculate it as the expected value of this T plus, and then we can calculate the variance and the test statistic based on this test. So this is from this guy, I think his name is Frank Wilcoxon. So he came up with this test in the 20s or the 30s. And he came up with the Wilcoxon sign rank test and the Wilcoxon rank sum test in the same paper. And so he came up also with the Wilcoxon rank sum test 2 years before the Mann-Whitney test. Mann-Whitney proposed the same thing. So that's maybe why I like to use Wilcoxon, but they're interchangeable. So if you hear Wilcoxon rank sum test and Mann-Whitney test, the same. But they're different than the Wilcoxon sign rank test. So exact tests do exist when there are not ties in the data. Otherwise, you have to say compare to a normal distribution, right? But now you're making the distribution about your assumption about the test statistic, not the data itself. So this is basically how we would calculate it if we wanted to do it kind of by hand. I'm just going to run this, and we'll output it. I'm not going to go through it line by line. So it'll give us our test statistic, standard deviation, and the p-value, 5.72. And then if we wanted to do this in R, there's a function called Wilcox.test. You pass in the variable. There's this options correction option, which we're going to set to false. Don't worry about that. For this, and it gives us back a test statistic and a p-value of 5.725. So, and the alternative, the null here is that the data, the median is 0 of the differences, and the alternative is that the median is not 0. And then if we wanted to say, do it with passing in both, we just say DST cell, and we say, give it one, and we give the other, we tell it it's paired. And then we say, ask for no correction. Now, as a reminder, we can see, look what this is with the t-test. So I don't think, okay, paired t-test. So you can see it gives very similar inference to the t-test, right? So the t-test was a p-value of 2.722 times 10 to the minus 5. Our Wilcox and sign rank test is 5.725 times 10 to the minus 7. So it's a little bit more quote unquote significant, but the inference would be the same. The decision would be the same. So in general, with non-parametric tests, they're not often more powerful than, say, a parametric test. They're going to be a little bit more conservative if the assumptions are met, but you don't have to make those assumptions, which is maybe nice. So, there's kind of a trade-off about whether or not you're willing to be a little bit more conservative and maybe lose a little bit of power. Okay. So the sign test is basically you take your variance. So if the data really is symmetric about 0, right? 50% of the data should have a sign less than 0. 50% should have 50% should be negative and 50% should be positive, right? If it's truly symmetric. So the sign test is basically just constructing a binomial test based on that observation. So you take the data, you say, hey, how many have a value greater than 0? And your total n is all the values that are not equal to 0, right? Because the values at 0 aren't going to tell you anything, so you get rid of them. So if we run that, we just use this binomial test. And it gives us, again, we would say, okay, we have evidence to suggest that it's different than 0. Okay. Any questions about that? So that's kind of a one sample, Wilcoxon sign rank test. You'll often maybe heard it called like a non-parametric t-test, right? Is maybe what some people will say, but that's what this is. Any questions on Zoom? Okay. All right, so next we're going to talk about the Wilcoxon rank sum test, or the Mann-Whitney rank sum test. So this is basically similar to a two-sample t-test, where we're going to basically see whether or not two populations come from the same distribution. So the only assumption here really is that they have the same variance. So people refer to it basically the same median is typically how people do it. And the way this is done is we calculate the ranks between the two groups, and we see whether or not the ranks are different or not. So we're going to look at that IgG GP41, and we're going to look at whether or not, whether by that engaging in unprotective receptive anal sex. So the steps are listed here. You take your values, you rank them ignoring the group, right? And then you calculate the rank sum for some group, and then you calculate their expected values. You calculate the number of distinct values, right? Because you have to account for ties. There's ties on your data. and then you calculate the variance. And then you can then calculate the test statistic by basically doing T1 minus the expected value divided by the square root of the variance. And then you compare to a standard normal distribution. Now there is a Wilcoxon rank sum, what's called a generalized Wilcoxon rank sum test when the variances aren't equal, but I have never actually seen it used in practice. But it does exist. I'm just not sure how often it is used. So we can calculate this by hand. We'll get a p-value of 0.2756. And then if we wanted to do this in R, I'm going to do the t-test again at the top, just so we can compare it to. Then we're going to do the Wilcoxon rank sum test on the bottom. Okay. So we can see our t-test of 0.2934. And then we can see our Wilcoxon rank sum test gives a very similar, and basically we draw the same inference. That we don't really have evidence to suggest that the median IgG GP41 differs between the two groups. Okay. Again, there is an exact p-value that can be calculated for this when there aren't ties. And there's also something called a conditional exact test that can be calculated, which is based on calculating all possible permutations. And so that's via this package called the coin package in R. So if there's no ties, this test will give us the exact by default. But if there's ties, it'll do this kind of approximation. So if I had put in here exact equals true, it's going to yell at me. It's going to say, or I thought it would. Oh, actually, so there's no ties in this data set. Okay, so bad example. There is no ties in this data set. So it's actually going to give us the exact test. So, and you can see right there, it now says Wilcoxon rank sum exactness, right? But you can see it's because this is a kind of a larger data set, it's very equal to the normal approximation. So 0.2774 to 0.2757 p-value. So if there are ties, it won't get to us. Okay. Any questions on that? I'm going to briefly talk about permutation testing. Okay. So there's another method we can use, which is based on permutations, or a kind of an MC p-value, Monte Carlo, like Markov chain p-value. And so what is done here is, so we have our test statistic, right, about whether or not we observe a difference. So what we can do is basically shuffle the labels, right? So let's say we have 100 people from group 1 and 100 people from group 2. We have our test statistic. And then we say, all right, what would be the test statistic if we shuffled it? So now like 50% of the people from group 1 we say are now from group 2 and vice versa, right? And then we calculate the test statistic. Again, do we observe something more extreme than what we did in our observed data? So the idea is if you permute the data a ton and you observe a lot of test statistics that are more extreme than what you observed in the data, that suggests that the null hypothesis, you cannot reject the null hypothesis, right? Because by simply shuffling the data, you're observing these extreme values, you're observing stuff more extreme, then you're likely that you likely don't have evidence of the alternative. Does that make sense? Oh. So the way we can do this in R is I'm going to take this data set. So right here I have a seed set. So this is when I shuffle, right? Because there's a random procedure here. We're shuffling them. So if you want, feel free to change that. We can see how different our results are. So I'm going to say set my seed, right? I'm going to say I'm going to do 10,000 shuffles. I'm going to tell it, here's what label I want you to shuffle. So that's at 0, 1 for whether or not they had this risk behavior. I'm going to say, here's our y, and then I'm going to make this vector of results, which I'm going to put the stuff in. So I then do a loop. So this is basically going to go from 1 to the length of this vector, so 1 to 10,000. And I shuffle that label. So let me show you what this looks like. So I've shuffled, right? So now, if we look at this, right? We can see what's been shuffled. So this first person, there's 0, but now we're saying like, what about if we mark them as 1 for that? And so on and so on. So this person got shuffled to the same group, this person did, but other people got swapped, right? We calculate the test statistic with that permuted value, and then we output the statistic. Okay? So if we run this, feel free to set a different seed. And then we look at the test statistic. So this is going to take a little while to run because we're doing 10,000 of them, but shouldn't take too long. So we get our observed test statistic. And then we basically take the minimum of which more extreme. So the number that are less than or equal to what we observe, or the number that are greater than or equal to what we observed. So that gives us a p-value of, it gives me, in this example, a p-value of 0.2684. So purely by chance, there was a lot of observations that were more extreme than what we observed. And if we wanted to plot it, we can see, so this is the distribution of all of my permuted test statistics, right? And we can see where the red line is. That's my observed. So you can see there's what our test statistic was based on how many were just more extreme, then we multiplied by 2. So like there's a lot of data that's more extreme than what we observed purely by chance from shuffling those labels. So this is another way that we can kind of test for whether or not the null hypothesis, whether or not we want to reject the null hypothesis. So just like, did anybody change their seed and get like a different result or slightly different results? No? My guess is if you do, it may be in the ballpark of 0.2684, but it may not be exactly that. But yeah, so this is another way that you can kind of test things in kind of a non-parametric kind of approach. So, any questions on that? Did anybody in Zoom set a different seed and get a slightly different p-value? Okay. All right. Yeah. Oh. No. Oh, maybe from one of the other code chunks? What is it saying? Yeah. Oh, dat AB doesn't exist? Yeah. Yes, so I think we define that in another code chunk. So if you just do control that. Would that be equal? Yeah, it's okay. Yeah, no worries. Yeah. Yeah. I'll go ahead and change the C real quick. So 0.2684, and then if I rerun this really quickly, you get 0.28888. So it's changed a bit, right? But the inference is the same. So we can see kind of what our distribution looks now. So yeah, so just another approach that can be used. And I think in R, I think the coin package can do this, but it's something you can kind of code up if you wanted to. Yeah, something to consider. All right. So there's no questions about that. We'll talk about power in the last bit of the session. So if you remember from earlier, power basically is, we talked about this type 2 error occurs when we fail to reject the null hypothesis when the alternative is true. And we typically denote this as beta. So the power of a test then is going to be the probability of rejecting the null when that alternative is true, which is basically 1 minus that beta. And this power depends on a bunch of different factors. The hypothesized value, like what is your alternative, right? So what is your mu A? So if mu A is further from mu naught, you're going to have more power. The hypothesized value of the null, what your type 1 error tolerance is going to be, the sample size, and then what's the observed variability of the data. And then what test are you actually going to use, right? So the power for a t-test is going to be different than the power for a Wilcox-Rank-Sum test. Okay. So for a fixed alpha and n, you compute the power for several values of the parameter, given the null hypothesis is false. And then, this is some power function that we have, and we typically graph it and have a power curve. And this typically goes into grants that you then ask for money. So, you say, all right, in this scenario, we'll have a power of blank to detect a difference of blah. And you kind of give that for a variety of values. Okay. So let's talk about population mean. So we want to study to determine whether or not the novel treatment has an effect on some secondary endpoints, say triglycerides. And if the triglycerides change by 10 milligrams, we want to be able to detect that change statistically. And we're going to do this via one sample t-test. So a previous trial tested a similar medication in a population showing a mean plus or minus standard deviation change in triglycerides of 15 plus or minus 80. So how much power are we going to have if our null is that the change is equal to 0 and the alternative is that it's not equal to 0? So even though we'll do a t-test in our final analysis, power calculations by hand are going to be easier if we assume a normal. They'll have a closed solution. So the way that we set this up is we say, all right, this is our test statistic. If we knew the variant, it's going to be y bar minus mu naught sigma divided by the square root of n. And that's going to be a normal with mean 0 and variance 1. Now, if we didn't know it, it'd be a t with n minus 1 degrees of freedom, right? And we'd have sigma hat there instead. So the probability of a type 2 error is going to be that we fail to reject the null when the alternative is true. So basically, our test statistic is not in the rejection zone. So it is going to be basically the probability that this z alpha over 2, this we're calculating the rejection, like that it's within that rejection area, within that kind of area that we were looking at here, right? Like it's in this red area, basically. This isn't a one-to-one, right? Because this is the t-distribution, but that's going to be our, what we're saying. Oh, I have simple linear regression still to go to. All right, so we basically can figure this out by hand, or we can say, okay, well, our test statistic is y minus mu naught, less than or equal, and then we add in, we kind of do some math, and we say, all right, beta then is equal to mu naught minus z1 minus alpha 2, and less than or equal y bar less than or equal to mu naught plus the thing, given the alternative is true. And so under the alternative, we know that y bar actually has a mean of mu a, right? Where that's the true unknown population mean. And then we can calculate this easily, right? We can just use any function. Heck, I think some like TI-83 calculators can give this to you. And so we can just calculate this for given mu a's, right? And given n's to see what our power will be. So if mu a equals 10, right, that's the true difference, we'll see that basically the probability of the type 2 error is 0.419, which means that we're only going to have power of 0.581, right? So kind of low. If, so we calculate that, 0.481, we can get the power as 0.58. So the power is going to be larger if the sample size is larger, if the population type, if the type 1 errors you're willing to accept is larger, and if the population variance is smaller, or if the magnitude of the difference between the alternative and the null grows, right? So we're going to have more power if like the true mu a is 40 than if it's 10. So yeah, more power to detect a larger difference than you do a smaller difference. Okay, so I'm going to show this for a variety of different data. So we can see kind of the power with increasing or decreasing a bar. So basically, if this is the mean here at 10, we have this pretty high, probability of a type 2 error in red. If the mean is actually at, this is at 15, right? We can see it's smaller. And then if it was, say, at negative 15, right, it'd be kind of in the same direction. So, and then we can also do this so we can calculate a curve for, say, different levels of sample sizes. So we can say, all right, if it's 0, we'll have basically, not a lot of power to detect the difference because there is none. It should be 0. And then as the true value increases, right, the alternative will have increasing power. And then as the sample size increases, we'll also have increasing power. So if we have 900 individuals, we're going to be able to detect a really small difference, right? We're going to be able to have power of basically 1 when we have a true difference of 10. When it's 200, maybe about 0.4, 40% power. So it all depends, and typically I think journals like to see like what is the power to observe when what do you have 80% power? I don't know where 80% power came, but I feel like I've seen that in a lot of journals or a lot of grants. People seem to do that, but you kind of have to base it on what are your monetary restrictions, right? How many actual observations are you going to be able to collect? what does the literature tell you that's out there about what the true difference is? And then you kind of have to figure out and play with these commands. And there's ways to do this in R, which we'll talk about. So same thing holds for if you're doing, say, population proportions, right? We can work it out and get some like closed probability. So here, this was the adherence. We can get the power, and given what we've observed, or what we speculate the true to be, and you can see it's basically 93% power to detect the difference. So, and then we can also calculate those curves to get an idea of like what our power may be, and with that sample size. So how do we do this in R? So there's a power package. There's a lot of other power packages out there. So the method that we'll talk about is this power.norm.test, where you give the effect size that you're interested in observing. So effect size is typically defined as the difference that you're interested in divided by the standard deviation. It's kind of a nice way to get around if you don't know anything about the standard deviation. There's this gentleman named Cohen who kind of gives what kind of effects correspond to a large effect versus a small effect versus a very small. So you pass in the sample size, you pass in the power and the significance level. So here we had that the mean difference was 10, the standard deviation was 80, we had 300 individuals. So if we run this, we get that the power is 0.582112, right, which is what we observed earlier. And then we can also give it a sequence. So if we say like, all right, give us the effect size for basically everywhere from -20 to 20 in a mean difference, right? We can then get the power. So we now have the power for all these different values. And then we can plot it. Say, all right, what does this look like, this power curve? And so we see the 1 minus beta, and then we have the alternative value here, and we can kind of get the power. So typically, I feel like what people do is they say, so we have this power, and you say, all right, which is closest? You go sort power minus, 0.80 or something along those lines, and try to find the closest to 80%. Or, where is your target power? So if you wanted, you can also have it solve. So if instead I left this blank, right, the effect size, I say null. I hope this works. If it doesn't, and then I say solve for 80%, it'll give us the effect size that we would have to observe, right? So this basically corresponds to, so remember this is mu alternative minus mu naught time divided by the sigma. Sorry, sigma here was 80. So if we multiply that by 80, that corresponds to a mean difference of about 12 or 13, right? So then there's all these other ones that you can use. 1 sample proportion test, 2 sample proportion tests, 2 sample proportion tests assuming unequal sizes, t-tests, ANOVAs, correlations, chi-squared, F, and so forth. And there's like a whole package function suites out there of people have made for certain design studies. So if you're doing like a random clinical trial or logistic regression or something along those lines, where you can figure this out. Okay. So for sample size estimation, things that may motivate this is, what your null and alternative. what is the smallest deviation from the null hypothesis that you want to be able to detect, whether or not it's a one-sided or a two-sided test, or kind of things that need to be thought about when you're like, what is the sample size that I'm going to need to detect this? So for the statistician, we have to consider the study design and what the test statistic is going to be. If we're testing the mean parameter, and then like how much do we want to control the type 1 and type 2 error. So if a 10 milligram difference is meaningful, clinically meaningful, then we want to be able to detect it, right? And so that's what we want to try to get the sample size to match that, to be able to calculate that. So if we want a high power, we may want to set it to 90%. Low, we want to maybe set it to 80%. And for estimating the variance, right, this is where we have to take in knowledge from the other populations, other studies, right? There's been a pilot study that's generated some data. We may want to use that. Or we may want to give a range of values to kind of hedge our bets. Okay. And then, for the T versus normal, it all depends on kind of the sample size that you're going to be gearing towards. So, and remember, if for large enough N, the T and the normal are going to be basically the same. Right. So, like everything, for a normal, it has a closed form solution where basically given some power that you want to detect, we'll have this form, and then you just kind of round up to the nearest whole number. So in our example, if we wanted to detect a difference of 10 with a standard deviation of 80 and we wanted 90% power, we would need 673 people. If I get this right. Okay. So let me see. So if we wanted D equal to 10 divided by 80, let's leave that null. All right. So you can see how I would do this in R is I just leave N blank, and it's going to solve for whatever you don't get. All right. There's also a closed form for when you have population proportions given here. And, to keep the sample size in R. So again, this is solving it for N. If you want to play around with that. You just basically leave the same blank that you wanted to do. So we'll run this. So the function, right, that we calculated by hand gave 672. Slightly different 0.4751. The mean power calculation with normal variance gave 672.4748. And then the one sample t-test one gave us 674.39. So 675 people, right? You can't recruit fractions of people. This isn't a stock exchange. So we can do the same thing for a one sample proportion, where we just basically leave that blank. So this es.h was a function, is a function to estimate the effect size. So didn't we define this? Yeah. So this will give basically how many observations we would need to detect some value. Okay. And that's in each group, if I recall correctly. All right. Any questions on that before I move into simple linear regression in the last 20 minutes? Sorry, y'all. I'll do better time management next year, so it won't impact y'all. But so simple linear regression. So this is a lot of the times when you're regressing two things on each other, it's very similar to just thinking of like whether or not two things are correlated with each other. So we're going to start there. There's non-parametric correlation, as there is anything, but we won't necessarily talk that. It's based on looking at the correlation of the ranks between two values. And the correlation and basically the questions that come with that fall into kind of these linear models. And so the testing in linear models typically depends on a normality assumption, which is what we'll kind of be talking about now, like classical linear regression. And then I think in the later classes, we may talk about logistic regression, but there's also Poisson regression, probit regression, negative binomial regression. There's a lot of different family out there. There's a good book called Generalized Linear Models, I think by Alan Agresti. It's maybe a higher level, but it really goes over most of these things. So, all right, correlation. So Pearson correlation is what we're going to be using to motivate this. So this is basically quantifying the linear association between two normally distributed variables. So we're not going to be talking about prediction, whatever, but just whether or not two things are correlated, right? What is the relationship? As one goes up, does the other goes up? As one goes up, does the other go down? As one goes up, does the other not care? So the assumptions required for this are that the two random variables are going to be normally distributed. For Pearson correlation, we have to assume that they're linearly related to each other. So if they're not, it won't necessarily detect something. So the non-parametric is called a Spearman correlation, which may be able to detect that. The correlation is typically detected by this like lowercase t, which is like a rho, Greek letter rho. So a value close to 0 suggests independence. A value close to 1 implies strong positive dependence. A value close to -1 implies strong negative dependence. So this rho is an unknown population parameter, and we're going to have to estimate it from our data. And it can be estimated as the covariance between the two x and y divided by their respective standard deviations. So it's unitless. So we basically removed any units related to this data. So this is going to give us a correlation, and it's going to be in between -1 and 1. It can only be within those values. So let's look at the correlation between CD4 to this, basically any envelopes of the CD107A and CD8 to any envelope. So this is basically in that efficacy study, we're looking at their CD107A cytokine response to any part of the HIV envelope. All right. So I'm going to take this data. I'm going to grab these two variables of interest. So CD4, any BRCC envelope, 107A, and CD8. I'm going to join it with that risk data, and then I'm going to filter to the group that received the vaccine. We're going to plot it, and we can see they look pretty linearly related, right? As one increases, the other seems to increase. So if we wanted to calculate this in R, I'm going to define XX as the CD4, YY as the CD8. I'll take the mean, so that'll be MX, standard deviation, SX, MY is the mean of YY, SY is SD, and then the length, right? And then we're going to calculate the covariance. So that's basically the sum of XX minus its mean times YY minus its mean divided by N minus 1. So that's going to give us a value of 0.766, which is, the covariance. So we could have also just gotten this by pressing this function COV, which stands for covariance. And then the correlation is going to be SXY divided by XX times SY. So here we cheated a little bit. So the reason why it's equal is the data has already been scaled to have mean 0 and variance 1 prior to passing it in. So that's why it's exactly equal. So if we look at Sx, it's 1. So there's a little bit of cheating here, but just so people are aware. All right, and if we wanted to do this in R, there's a function called COR, correlation. We give the two values, say the method is equal to Pearson, right? And it gives us a correlation of 0.766. All right. Okay. Now, so simple linear regression, we're going to give some definitions. So the first off, typically what people denote the dependent variable. So this is kind of sometimes people call the primary outcome. So the outcome, response, y. And we want to know how it changes as some independent variable x changes, right? So the independent variable is also sometimes denoted as the primary exposure, the predictor, the risk factor, the environmental factor, often denoted by X. In experimental studies, it may be something that's controlled by the investigator, right? So like the vaccine status, right, was kind of set by the investigator, or, you know, what food pellets you gave to mice in your lab, and so on. So regression is looking at the relationship between this normally distributed dependent variable with a bunch of independent variables. So here the main assumption is normality is on the y. And we want to estimate kind of the relationship between the dependent and the independent values. And we're going to focus on a linear relationship. So the assumptions are our explanatory variable needs to be fixed or given. It's measured without error. That's a big assumption. There's a whole class of statistics devoted to measurement error, right? So people may underreport their height, or the machine you're using may be wrong, right? So there's methods out there for trying to account for that. For each value of x, there is some population of y that exists that is normally distributed with the same variance, and everybody's independent from each other, right? So all the observations are from different people that maybe there's no way that their y's can impact each other, right? If that assumption isn't met, there's other methods that can be used, such as linear mixed effects models or generalized estimating equations, but those aren't going to be covered in this class. So when the model assumptions are met, we will typically write this out as being y is equal to beta naught plus beta 1 times x plus some error. So beta naught and beta 1 are the regression coefficients, and error is some error term that we assume to be normally distributed with mean 0 and variance sigma squared. All right. Now, just out of curiosity, given that we know that the data we're going to be using are scaled already to have mean 0 and variance 1, what do you all think beta naught is going to be? The intercept. All right, but we'll get it. So it's probably gonna have a mean of 0, right? Because we've already scaled everything to have a mean of 0. Yeah. So for a simple linear regression, the estimation is basically what we're doing is minimizing the ordinary least squares. So we're taking basically the summation of yi minus the expected mean, so the beta naught, beta 1 squared, and we try to find a beta naught and beta 1 that minimizes that. All right. And like everything, it has a closed form solution. So beta 1 hat is going to be equal to sxy divided by sx squared. So the covariance divided by sx. And beta naught hat is going to be equal to y bar minus beta 1 hat X bar. So in this example, where we've scaled everything, beta 1 hat is going to be the correlation, right? And then beta naught hat is going to be y bar. Y bar is 0 in our case. And then X bar is also 0. So it's going to be 0 in our case. Yeah. So if we wanted to estimate it in our example, at beta 1, we get 0.766. And then if we look at beta naught, it's going to be B0. Okay. And if we wanted to do this in R, this function called LM, I always think it's linear model. And we say just pass the Y, and we pass the variables on there, the right. And if we look at this, so we can see what it gives us. So we had our B1 as 0.766. Our beta naught is practically 0, right? That's a rounding error. And then it gives us the intercept. So you can see the intercept is kind of different to the 10 to the minus 18th degree, but that's livable, right? That's basically 0. Thank you, Lauren. And then we have the similar CD beta 1. Okay. So how do we interpret these? So beta 1 hat is the slope of the regression line that says that the log 10 scaled CD8 value increases on average by 0.76 for every 1 standard deviation increase in the scaled CD4 value. So as one value goes up, the other goes up. So an alternative way is if we compare two people who only differ in CD response by 1 unit, we would expect that the person with the 1 unit higher value will have a CD8 response that is 0.76 value higher. All right. Beta naught, the intercept is looking at whether or not amongst those that have a 0 value of that log 10 scale, the average CD8 would be 0, right? Which isn't super useful in this example, right? And typically the intercept isn't useful. So like if this was say age and BMI, right? Like say age was the outcome and BMI, like you can't have a BMI of 0. So if X equals to 0 is a meaningful value, then the interpretation of the intercept is meaningful. If not, it is not meaningful. It's just something that we kind of have as help center the data. Okay, so there's a good amount of assumptions that are required. So we want to make sure that we see the data looking kind of following, our QQ plot. And then we also want to plot the residuals versus the fitted values and see basically no pattern here. So this is a good fit, all right? So I'll show a bad fit. So this is a bad fit. So you can see it looks normal, right? But if you look at the residual pattern, you see a pattern, right? So you kind of. And then if we look at ours, maybe not great, but for the sake of this exercise, we'll deal with it. Okay. And then to test, there's looking at the variance explained and kind of, you can then construct a test statistic. So in R, if we took our regression model, so this is kind of the formula that you would use, and it follows a t-distribution with n minus the number of parameters you've estimated. Here, 2, the intercept and our main variable of interest. But if you do summary of the out, which is what we define the LM object, it'll give us this table of basically the estimate, the standard deviation, and then the resulting p-value. So this will correspond to doing a correlation test as well. So if we did correlation test in R between those two, it'll line up with what's in the linear model. Yeah. Now, due to time, I'm not going to go through the two-sample linear regression. I apologize. So feel free to go through that. But basically here, what it's going to correspond to, let's say if we had our explanatory variable was a binary, right? So it's yes or no. So in here, unprotected receptive anal sex. That's going to correspond to a t-test, where we're comparing the means between two groups. So unfortunately, I won't have time. It's all here for people to go through, but we do have a survey to that we would like people to do if possible with the kind of remaining time. This is super useful for us for kind of improving the lectures and reporting to the NIAID about what we're doing. So there's a link here to the Qualtrics form. It shouldn't take too long. It's basically some information about, how did you participate? And then, there's some specific questions related to today's session. So just click on today. And this is super helpful for us for reporting and also for, continuing to improve and work on these lectures. So if there's any questions, I'll stick around, but we'll go ahead and end it there. And I'll copy the link into the chat for people. So just, yeah, thank you all so much. And yeah, any questions, please let me know.